In this video, we'll be going over what electron configurations are and SPDF notation. So let's say I have the atom oxygen, right? And it has an atomic number of 8. So since the atomic number is 8, it has 8 protons and it needs 8 electrons to have a neutral charge, right? Because protons are positive and electrons are negative. In the model of the atom, right, you have the nucleus. Let's say this is the nucleus of oxygen. Electrons orbit around this nucleus in what are known as electron shells, right? So for oxygen, right, we'd have 2 electrons in the first shell, and then 6 electrons in the second shell to make up a total of 8 electrons. So if we want to write the electron configuration of oxygen, we would use SPDF notation. So what does that mean, right? So each shell of oxygen has subshells in it. So for the first shell, it's going to have the subshell of 1s2. So that's going to be the only subshell in it, right? For the second shell, it's going to have 2s2 and 2p6. So what do I mean when I say 1s2, right? So I have 1s2. So the first number, that's going to mean the electron shell that subshell is in. So 1s2 is going to be in the subshell of the first shell, right? The letter, right, that represents the type of subshell. So in this case, the subshell is S. And the exponent over here is how many electrons that subshell can hold. So as we can see, right, in the first shell, there's only the 1s2 subshell. That's only going to hold 2 electrons. That's why the first shell of oxygen only has 2 electrons, right? So for the second electron shell, we're going to have 2s2 and 2p6. So the difference between the p subshell and the s subshell is that the p subshell is going to be able to hold 6 electrons, right? So if we wanted to write out oxygen's electron configuration, what we would do is we'd write 1s2. We're going to draw this diagonal arrow downwards. 2s2, draw this diagonal arrow downwards. It'll come important later. 2p4. So the reason we're putting 4, right, is because even though it can hold a maximum of 6 electrons in the subshell, we only need 4 because oxygen has 8 electrons, right? You add up the exponents, 2 plus 2 plus 4 equals 8. Let's say we try this with an atom that's a little bit more complex. So the example I'll use of a more complex atom will be bromine. It has 35 electrons. So how are we going to represent that, right? So in the first shell, they're going to have 1s2. Second shell, 2s2, 2p6. In the third shell, we're going to have 3s2, 3p6, 3d10. And in the fourth shell, we're going to have 4s2, 4p6, 4d10, and 4f14. This is why this is called SPDF notation, right? We have S, P, D, F. And you can use this to remember the order. So if we're going to write the electron configuration of bromine, we're going to go 1s2, 2s2, right? Remember the diagonal arrows. 2p6. And then because this arrow goes to 3s2, we're going to go 3s2. And then 3p6, right? And this arrow is going to go to 4s2. So instead of going to 3d10, because the diagonal arrow leads to 4s2, we're going to do 4s2 first. So 4s2, then we're going to go to 3d10, because the diagonal arrow cannot go any further. 3d10. And at this point, we're at 30 electrons in these subshells, right? 2 plus 2 plus 6 is 10. 2 plus 6 plus 2 is 10. And then we have another 10. So 3 10s, 30. So for this 4p6, right, following the diagonal arrow, it only needs 5 more electrons to finish 35. So the electron configuration of bromine in SPDF notation would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p5. Now I'm going to show you a trick with the periodic table. So I have my periodic table here, right? So the periodic table is really, really handy because it makes it easy for us to find out electron configurations, right? So we have the first row, right? The first period. This is going to represent the first shell. So since the first shell is 1s2, it's going to be 1s2, right? For the second row, the second period, it's going to be the second shell, right? So 2s2 and then 2p6. Third row is going to represent the third shell, right? So we have 3s2 and then 3p6. And it's super important to note that 3d10 is not here. So remember how we were going diagonal? So we have 1s2, we go diagonal, right? 2s2, we go diagonal. 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 4f14. We go diagonal from the 2p6, we get 3s2. We go to 3p6, right? Because the diagonal can go no further. We go diagonal again. And instead of going to 3d10, we go to 4s2, right? So this is why 4s2 is ahead of 3d10. So this is going to represent 3d10. And then this over here is going to be 4f14 and 5f14. So what this does is it makes it really, really, really easy for us to figure out electron configurations, right? So let's say I want to figure out the electron configuration of iodine, right? Iodine's right over here. So this is super easy for me to do. I go 1s2, this is 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, remember this is 3d10, 4p6, 5s2, 4d10, right? This one is 3, so this one is 4, and then 5p6. So that's how the periodic table can be used to find electron configurations. It's super useful. It's a lot better than using this method over here if you have a periodic table that you can use.